This is Professor Deref Seitz. Graphs, real number plane. How can we visualize numeric relationships? Starting with the most basic concept, we can use ordered pairs. And then we can move on to equations and things called functions. Here's a picture showing something that has 4 quadrants with shadows making interesting shapes. Real number plane concepts. The real number plane is measured by 2 perpendicular real number axes. The horizontal axis is called the x-axis. The vertical axis, which is perpendicular to it, is called the y-axis. The 2 axes divide the plane into 4 quadrants. Ordered pair relationships are represented by points with coordinates x and y. X is the horizontal location or coordinate of the point, and y is the vertical location / coordinate of the point. A rectangular grid facilitates placements. The real number plane is a two-dimensional, 2D world. For this reason, it is sometimes referred to as R2. Here we have the real number plane. The horizontal axis is the x-axis. The vertical axis is the y-axis. On the x-axis, it's a real number line. Positive numbers increasing to the right, negative numbers decreasing to the left, becoming more and more negative. 0 is where the 2 axes intersect, the vertical and the horizontal. The y-axis increases up and the negatives are down. The quadrants that are divided by the axes are labeled in a counterclockwise manner: quadrant 1, 2, 3, and 4. Some ordered pairs are shown here. Ordered pairs use parentheses, the x-coordinate, comma, and the y-coordinate. Here we have 2, 2. It's 2 on the x and 2 up, so 2 over and 2 up. 2, 2 is that point, that ordered pair. 2, 3 is 2 from the origin. It's 2 over to the right and 3 up. That point right there, they're stacked on top of each other vertically, those 2 points. 5, 0 lies on the x-axis. It's 5 units on the x and 0 units on the y. The origin, of course, 0, 0. Here's a point, a real number. It's not a real number, it's an ordered pair of real numbers. This point, 0 and negative 1. 0 on the x and negative 1 on the y. Negative 5, 2 in quadrant 3, negative 5, negative 2. And over here, negative 5.5 and 3.25. Points do not have to be located at the intersection of the grid. The grid is just to facilitate to see where things are at. A point can have any real number coordinates for the x and for the y. It's a rectangular grid. And we have on the right, extending out, positive infinity, and on the left, negative infinity. On the top, positive infinity. On the bottom, negative infinity. Here we see some points graphed as ordered pairs. Visually, we can see them. Some random ordered pairs are shown here. Notice, since they're random, it's not surprising they have no real pattern. Just wherever they happen to fall. Here are some more points, a finite number of points, and they are somewhat in what's called a linear pattern, looking somewhat like a line. They're not in an exactly straight line, but they have that general pattern. Equations bring order. The solutions of equations in X and Y illustrate relationship patterns. A solution set is all the ordered pairs with XY coordinates that make the equation true. You plug in the value for X and plug in the value for Y. When you make those substitutions, you will have a true equation. The left-hand side will equal the right-hand side. The set of all the solution X coordinates, all the X's in your solution set, is called the domain of the relation. The set of all the Y coordinates in the solution set is called the range of the relation. Equations maintain equality relationships. Equality relationships are balanced relationships, and balance brings order. Here are some linear relationships introduced by various linear equations. These are equations in the variables X and Y, which represent the horizontal and the vertical offsets from the origin. And notice this one here, 2x plus 3y equals 1. All these points that solve that equation line up on this line, perfectly lined up. Here's a line over here, x equals y. It goes right through the origin. And notice, for example, the ordered pair 1, 1 is on it, 2, 2, 3, 3. Notice the x and the y's are always equal. -3, -3, x equals y. Y equals 2. Every point on this line right here, this horizontal line, has a y coordinate of 2. It doesn't matter what the x is. Y equals 2 defines that line. A vertical line, x equals -5. Doesn't matter what y is. Y can vary. X is -5, and all those points line up on that line. Linear relationships introduced by linear equations. Quadratic relationships. Here are two equations, y equals x squared, equations in x and y, using a second degree exponent, making it quadratic in the sense of like a quadrilateral, a two-dimensional geometric object. And here's another one, x minus 1 equals parenthesis y plus 2 squared. Look at what you get for these quadratic equations. Order. They're continuous, unbroken, and smooth. This is not random chaos. From these equations that are visually represented here, when you see the equation, you see a symbolic mathematics. When you see its graph in this two-dimensional plane, you now have ability to use your visual thinking to infer various kinds of relationships, such as symmetries and minimums and various kinds of things that you can't immediately see from the symbols. Using the same two graphs, we introduce now the concept of a function. When you have an ordered pair, you can think of the x as a question and the y as an answer. For functions, every question, every x, has exactly one answer. So in that case, y is equivalent to a single valued formula involving x. When we ask the question with x, x is called the independent or question variable, and the answer y is dependent, because whatever question you ask, it has one answer. There's no choice there. The choice is in the question. Independent and dependent variables. Looking at y equals x squared, this graph, for every question, there's exactly one answer. 1 is 1. For the question 2, it's 4. For -2, it's 4. It doesn't matter if two different questions happen to have the same answer. The key point is that every question has exactly one answer. This horizontal version of this curve over here, these are called parabolas, by the way, is just fine as a relation, but it's not a function. Why? If you ask about 5, there are 2 points that solve it. You can see them here. 5, 0 is a solution, and 5, -4 is a solution. There's 2 answers to the question 5. So it does not qualify as a function. There's a convenient geometric test that you can apply called the vertical line test to determine if a relation, if a general graph is a function or not. If you can draw a vertical line that intersects the graph in 2 or more points, then it is not a function. This one over here, every vertical line hits it in just 1 point. These parts up here, they go off, up, and they continue to move out towards positive infinity and negative infinity because you can square x for any x on the whole x-axis. This equation down here, the one that's not a function, if you rearrange it to get y by itself, you will get y is plus or minus the square root of x minus 1 minus 2. So for every y, even algebraically, you see that there are 2 answers. Double quadratic relationships, when both variables are squared, you get, again, amazing order, continuous and smooth relations. Notice that these 3 relations here, none of them is a function. None of them passes the vertical line test. However, they're very important relations that come up in the real world for various physical behaviors in the world. Rational relationships. Rational is a ratio, a fraction. This is a single graph here, single relation defined by the product of x times y equals 1. Every point on this graph, no matter where it is, has this property that the product of the 2 coordinates equals 1. A couple examples, 1 and 1 here is 1, here -1 and -1. Here 2 and 1/2, 2 over and 1/2 up is 1. You can rearrange this equation by dividing both sides by x or dividing by y and write it in equivalent forms. Y is 1 over x and x is 1 over I. However, keep in mind now, since x and y appear as denominators in these alternate forms, we know that x can't be 0 and y can't be 0 in these alternate forms here. Looking at this graph, and why can't they be 0? Because division by 0 is undefined. You cannot have a 0 in a denominator. It's not allowed. And the graph, the single graph, obeys this law. The x-axis, this horizontal line right here, the x-axis is a limit line, also known as an asymptote, where the value of y would be 0. Y can't be 0 because if you had a 0 in the product, it could never equal 1, and you'd have a 0 denominator. So the graph will never touch the x-axis. It's a limit line. It gets closer and closer to it on both sides as you get to bigger and bigger x's and smaller x's, but will never touch it or cross it. And similarly, the graph is broken vertically by the y-axis, also a limit line, because there x is 0. And we know x can't be 0. That would not give us a product of 1. So the graph visually obeys and exhibits the relationships and the restrictions of those relationships. Root relationships. Here are two different graphs. Y equals the square root of x in green here, and x equals the square root of y. Again, equations in x and y shown here. This dashed line here is the line y equals x. We looked at that before. And we notice for these two graphs, both of which happen to be functions, as you can see, that there's an interesting pattern. You have the point 4, 2 here on y equals the square root of x. Let's look at that. If x is 4, then y is the square root of 4 is 2. Here, if x is 9, then y is the square root of 9, which is 3. Square root of 1 is 1. On the other graph, where x is the square root of y, if you have x is 2, as in here, then it has to be the square root of y, and y has to be 4, because the square root of 4 is 2. 2, 4, 4, 2. They're reflections of each other across this diagonal line. 3, 9, 9, 3. 1, 1, 1, 1. They both are there. These are known as inverse functions. They're inverse operations. X equals the square root of y, this one right here, is equivalent to, if we square both sides, y equals x squared, where x is restricted to be greater than or equal to 0, because you're taking it equal to a square root. Square roots cannot be, this is the principal square root, cannot be negative. And so the domain of this blue function here, all the possible x's, goes from 0 to infinity. And you can see that it starts at 0 and it moves out. And its range is the same thing. It starts at 0 and goes up. The domain of this other one over here and range similarly goes from 0 to infinity for the x's and also the y's. This keeps going up and up, higher and higher, but very slowly. These two functions are mirror images across this diagonal. They're inverse functions, inverse operations. So these patterns can be seen visually, not just analyzed through the algebra. Exponential and logarithmic relationships. This green graph is a graph of 2 to the x power. Notice here that the x appears in an exponent position. That's why it's an exponential equation. And this other one happens to be the inverse of that one, and it's called the logarithmic function. And they both have a base associated with them, in this case base 2. It's 2 to the x and log base 2 of x. They both happen to be functions, past the vertical line test, and they're inverses of each other. A logarithm is an exponent. It's the exponent that you have to use in order to raise the base to that power in order to get whatever's in the parentheses here. So for example, if we're dealing with this logarithm here, and we have this 0.42, and we're trying to find what exponent do we have to use on 2 in order to get an answer of 4, we have to use 2, right? The logarithm, the exponent has to be 2, that's the log, the y value, in order to put that as the exponent on the base 2 to get the 4, which is the question variable. 4 is the question. We're dealing with log base 2, and the answer is 2. It's much easier to see with the exponentials. If you have 2 as the x, that's in the exponent, so 2 squared is 4. Very straightforward. Logarithm being the inverse, you have to think backwards. That's how things work in mathematics frequently. You have something that goes in one direction and its inverse, if it has one, takes you back to the starting point, going the other direction. There are some formulas in the real plane that are basic and useful. Two of them, the distance formula and the midpoint formula. The distance formula, to find the distance between any two ordered pairs with, say, coordinates x1, y1, x2, y2, and let me point out these subscripts here are just giving us a variety of variable names. They are not any kind of mathematical operation. This variable is called x1 and this one's called x2, and it reminds us that these are x coordinates. So x1, y1, x2, y2, the distance between these 2 points is from the Pythagorean theorem that this is derived, is the square root of the difference in the x's squared plus the difference in the y squared. Here's an example. The distance between 2, 4 and 5, 8. Difference in the x's, 5 minus 2 squared. Differences in the y's, 8 minus 4 squared. That's 3 squared plus 4 squared, 9 plus 16. We're dealing with square roots here for the distance. Square root of 25, 5. The midpoint formula between 2 points, indicated by M, gives you the point halfway between them, straight lined a segment between them, is the sum of the x's divided by 2 for the first coordinate, the x coordinate, and the sum of the y coordinates divided by 2 for the second coordinate. Using the same 2 points that we used over here in calculating the midpoint, 2 plus 5 over 2 and 4 plus 8 over 2, that's 7 halves, and 12 halves is 6, 7 halves 6.